Most modern front-end applications rely on server-side rendering, pulling data from databases and generating HTML before sending it to the user. This architecture relies on large, centralized server farms to process those requests. When a user clicks a link, that request travels over the network to a central provider, hitting a service like AWS Lambda. To handle that single request, the provider must allocate physical hardware resources, boot up an operating system container, and then initialize a complete Node.js runtime environment. All this initialization takes time, creating cold start latency, a period where the server prepares to work rather than executing code. Because the server is booting up, the user's browser is left waiting. This accumulated delay directly penalizes your time to first byte. You can deploy these containers to multiple regions, but requests still have to travel hundreds or thousands of miles to reach the nearest data center. The physical speed of light places a hard limit on how fast a centralized server can reply. Traditional serverless architecture offers massive backend scale, but the heavy container boot sequence and geographic distance make it a poor fit for modern user interfaces that demand minimized latency. To reduce latency, execution logic is migrating to the edge. Instead of central data centers, code deploys to a dense network of local routing nodes, processing requests within milliseconds of the user. But these edge platforms cannot deploy full Node.js containers to thousands of local nodes. The compute overhead would be impossible to maintain. Instead, they execute code using V8 isolates. This is an architecture built on the browser-native Web Worker API, completely discarding the standard Node.js backend environment. An isolate is a single, pristine JavaScript context. Multiple isolates run simultaneously inside a shared host process, removing the need for separate OS containers. Because the host is already running, spinning up a new isolate skips the boot sequence entirely. Startup times disappear. Achieving this millisecond-scale backend response means developers must leave the standard Node runtime behind and write code tailored for a different kind of environment. The speed of the isolate model comes with a strict architectural trade-off: aggressive resource limitations. To maintain thousands of instant execution contexts on a single machine, edge workers are typically confined to a rigid memory sandbox of around 50 megabytes. This creates a direct collision. Developers have incredibly fast execution times, but face severe constraints processing large payloads within that tiny digital footprint. Consider a standard enterprise task, like fetching a 100 megabyte product catalog or analyzing a massive JSON log file directly on the server. In a traditional serverless container, this is trivial. These functions can be provisioned with up to 10 gigabytes of RAM, easily swallowing massive files. Inside an edge worker, memory capacity becomes the primary bottleneck determining what your application can achieve. Attempting to load that 100 megabyte catalog using a synchronous blocking command like await fetch instructs the JavaScript engine to parse the entire response into memory all at once. The incoming payload quickly exceeds the 50 megabyte allocation. The isolate hits its absolute limit, resulting in a catastrophic out-of-memory crash. As the documentation explains, a promise represents the result of an asynchronous operation. Once it settles, its value is fixed. Because standard promises represent a single final result, they must wait for the entire payload to arrive before settling. To process large files at the edge, you have to implement backpressure, a concept originally designed into the core philosophy of Node.js. Backpressure is the practice of reading and processing data in small, sequential chunks. By managing the flow rate, the full dataset is never held in active memory at once. Operating in an edge environment requires discarding the habit of single-shot memory loading in favor of continuous stream processing. The solution to handling massive payloads in a tiny memory footprint relies on treating the data as continuous incoming streams. JavaScript provides a built-in interface for this, the readable stream object, which represents a source of data that you can read sequentially. With the ES 2018 specification, web streams received a critical upgrade. Readable stream objects were made asynchronously iterable. This allows developers to process the stream using a specific syntactic structure, the for await of loop. Inside this loop, the runtime yields a distinct promise for each individual bite-sized chunk of data as it arrives over the network. The JavaScript engine resolves the promise, processes that specific chunk, and immediately discards it from memory before the next promise in the sequence resolves. This asynchronous iteration syntax acts as a pressure release valve, automatically breaking massive backend payloads into safely executable microtasks. Instead of accumulating those chunks on the edge server, you can pipe this processed stream directly back into the response sent to the client's browser. This triggers progressive rendering. As the first chunks of HTML and data arrive, the browser begins drawing the user interface immediately, rather than waiting for the entire request to finish. This chart tracks the live memory consumption of an edge worker. As a 100-megabyte dataset streams through the for-await of loop to the client, the memory usage stays completely flat, sitting well under 10 megabytes. Because each chunk is processed and yielded sequentially, the V8 engine performs aggressive garbage collection instantly, maintaining that flat line regardless of the total file size. By streaming the response, time to first byte drops significantly. The client renders the first piece of data while the edge worker is still fetching the rest. This highly responsive execution flow stands in sharp contrast to the heavy, slow, containerized cold starts of traditional centralized servers. Achieving these metrics requires abandoning synchronous, blocking backend programming logic. Mastering the edge means re-architecting JavaScript to stream flawlessly, allowing massive applications to run safely within a 50-megabyte sandbox.